Carbon capture and storage, mitigating climate change introduction. As the world faces the increasing threat of climate change, reducing carbon dioxide, CO2, emissions has become a global priority. While transitioning to renewable energy sources is essential, it is not enough to meet emission reduction targets on its own. Carbon capture and storage, CCS, offers a powerful solution, enabling industries to significantly cut their carbon footprint by capturing and storing CO2 emissions before they reach the atmosphere. CCS is a technological process that captures CO2 from industrial and power plant emissions, preventing it from contributing to global warming. Once captured, the CO2 is transported and permanently stored in deep underground geological formations, ensuring long-term containment. This technology provides a bridge to a low-carbon future, allowing industries to continue operations while working towards sustainability. How carbon capture and storage works. CCS consists of three key stages: carbon capture, transportation, and storage, each of which plays a crucial role in reducing emissions effectively. Capturing carbon dioxide. There are three main methods of CO2 capture, each designed for different industrial applications. 1. Pre-combustion capture. CO2 is removed from fuels before combustion, typically used in gasification plants. 2. Post-combustion capture. CO2 is extracted from flue gases after fuel combustion, using chemical solvents to separate it. 3. Oxy-fuel combustion. Fuel is burned in oxygen instead of air, producing an exhaust stream primarily composed of CO2 and water vapor, making capture easier. Transporting captured carbon. 1. After capture, CO2 is compressed into a liquid state for transport via pipelines, ships, or trucks to designated storage sites. 2. Pipelines are the most efficient means of large-scale CO2 transportation, leveraging existing infrastructure similar to that used for natural gas. Storing carbon safely. 1. Captured CO2 is injected into deep underground geological formations, such as depleted oil and gas fields or saline aquifers. 2. These formations act as natural storage reservoirs, ensuring that the CO2 remains securely trapped beneath impermeable rock layers. 3. In some cases, CO2 is used for enhanced oil recovery, EOR, where it is injected into oil fields to increase oil extraction efficiency while simultaneously storing the CO2 permanently. The role of CCS in climate change mitigation. While CCS alone cannot solve climate change, it plays a crucial role in reducing emissions across industries where alternative solutions are not yet feasible. Reducing industrial emissions. 1. Heavy industries such as cement, steel, and chemical manufacturing generate significant CO2 emissions that cannot be easily eliminated. 2. CCS allows these industries to operate with reduced environmental impact, buying time for further technological advancements. Decarbonizing power generation. 1. CCS enables coal and natural gas power plants to significantly cut emissions while maintaining electricity production. 2. This technology supports the transition to renewable energy by providing reliable backup power during periods of low renewable generation. Achieving net zero emissions targets. 1. Many countries have committed to net zero emissions by 2050, a goal that requires CCS to capture and store unavoidable CO2 emissions. 2. CCS can be combined with direct air capture, DAC, to remove excess CO2 directly from the atmosphere. Challenges and limitations of CCS. Despite its benefits, the widespread adoption of CCS faces several hurdles that need to be addressed. High costs and energy demand. 1. CCS requires significant investment in capture technology, transportation infrastructure, and storage facilities. 2. The process is energy intensive, potentially offsetting some of the emission reductions unless powered by clean energy sources. Storage risks and public perception. 1. Concerns about CO2 leakage from underground storage sites exist, though studies show that properly selected and monitored sites are highly secure. 2. Public opposition to CCS projects often stems from misconceptions about safety and long-term viability. Regulatory and policy barriers. 1. Many governments lack the necessary financial incentives and regulations to support widespread CCS deployment. 2. The success of CCS depends on carbon pricing mechanisms, subsidies, and clear policy frameworks to encourage investment. The future of carbon capture and storage. Ongoing advancements in CCS technology are making it more efficient, cost-effective, and scalable, increasing its potential as a key climate solution. Africa, carbon utilization innovations. Research is exploring ways to convert captured CO2 into synthetic fuels, construction materials, and chemical feedstocks, creating economic value from emissions. High voltage sign. Integration with renewable energy. CCS can be combined with bioenergy with carbon capture and storage, BECCS, to generate negative emissions, actively removing CO2 from the atmosphere. Building construction, expansion of CCS infrastructure. Governments and industries are investing in shared CCS networks, allowing multiple facilities to benefit from centralized storage and transportation. Scroll, stronger climate policies. As more nations commit to carbon neutrality, increased funding, incentives, and regulations are expected to accelerate CCS deployment. Conclusion. Carbon capture and storage, CCS, is a critical tool in the fight against climate change, providing an effective way to reduce industrial and energy-related CO2 emissions. While challenges such as high costs, public perception, and regulatory hurdles remain, continuous innovation and strong climate policies will determine the long-term success of CCS. By integrating CCS with renewable energy and emerging carbon utilization technologies, the world can take significant steps toward achieving a sustainable, low-carbon future.